So welcome to lecture 2. In this lecture, let's start with hydrolysis of acetals. So acetals, we'll also see imines, and we'll see enamines. So what are acetals? So acetal is a compound where you have OR groups attached to a single carbon in place of the ketone. So remember that on dehydration we end up getting acetal. So acetals form under dehydration of ketones or aldehydes. So you get them when you have dehydration of ketones and aldehydes. Now let's take an acetal and let's say we hydrate. What will happen? So the hydration of an acetal eventually results in the same process of getting a ketone back again. Plus you end up getting alcohol, primary alcohol, 2ROH. So what is going to happen here is these two bonds are going to break, and each of the bond is going to take up one hydrogen and the oxygen will go into that place. So this is the rudimentary form of the reaction that's going to happen. So we call this reaction hydrolysis reaction, and this reaction only occurs under acidic medium, so which means that it is not going to occur under basic medium. So when you have a basic medium, say for example so plus H2O, in the presence of NaOH there is no reaction. So this reaction is an acid catalyzed hydrolysis. So this is an acid catalyzed hydrolysis reaction, not hydration. Remember the difference between hydrolysis and hydration. Hydrolysis here is addition of water, that's it. Hydration is adding of OH groups. So that's the difference between these two processes. Now let's look at the mechanism in which this acetal becomes ketone. So let's look at the first mechanism and let's see how the mechanism actually works. So first you have an acetal. So the acetal first, in presence of H3O plus, which is found by the acid, undergoes a proton transfer, where the OR group, the oxygen, generally has 4 electron pairs. Now that attacks the hydrogen, and the hydrogen gives its electrons back to oxygen. So this results in the formation of an intermediate group which looks somewhat like this. So on one side we have OR, and on the other side what will happen now is the hydrogen is also attached to the oxygen, and there is an R group here, and this results in you have 2 electrons here and there is a positive charge on this oxygen. And what will happen now is the oxygen that you have here has 2 electron pairs, so it donates 2 electrons to the bond, and the bond ends up giving its bond back to the oxygen, so resulting in the removal of this ROH group. So removal of this ROH group. So this then, so when you remove minus ROH, so now what do you have left? So you have a double bonded oxygen that is bonded with an R group and positively charged, because it still lacks one of the electron pairs. Now it undergoes a nucleophilic attack by a weak nucleophile. So this compound now undergoes a nucleophilic attack by a weak nucleophile. So the weak nucleophile that attacks here is water. So the oxygen here attacks the carbon, and these electrons will go back to oxygen. So on one side you have oxygen with 2 electron pairs and an R group, and on one side you have OH, oxygen with 2 hydrogens and a lone pair of electrons with a positive charge. So what happens next? So next, notice because of the positive charge and because it's in an acidic medium, this compound now again gets attacked by another water molecule, but this time the water molecule does not want to actually attack, it rather wants to undergo proton transfer because it's in an acidic medium. So it attacks the H group, and the H donates its electrons back to oxygen, so resulting in the formation of OR, and on this side you have OH. So notice that there is an OH group and an OR group, because notice that this is removed. So now you have an OR and an OH. So whenever you had OR and OR, we called this an acetal. So this is called an acetal. And here there is an OR group and an OH group. So this is called a hemiacetal. So we call this a hemiacetal. Now the hemiacetal undergoes further reactions in presence of H3O plus again. I'm going to write the full reaction for one of them just so that you understand everything. So what happens here now? This H3O plus group, so the OR group that is present here again attacks the proton, and this results in the electrons going back again. Again, remember that the exact same thing is happening. So what happens to one OR group? So one OR group also happens to the other OR group as well. So this results in the formation of a double bond. So O, H on one side, R on one side with 2 electron pairs and a positive charge. And on this side you still have the OH group. So this is the idea behind here. Now what will happen here is that this compound now donates its electron pair here. So this donates its electron pair here, and this electron pair, once it goes here, this goes up to the oxygen, resulting in the removal of this ROH group. So now when you write down the reaction, you will get a double bonded OH with a single pair of electrons and a positive charge. So in this process minus ROH is happening, so there is ROH removal. Now another water molecule again will end up coming to the structure here. So if you take another water molecule here, so this water molecule now attacks the proton, and the proton ends up giving the electron pair back to oxygen. So this electron pair attacks the proton gives its electrons back to oxygen, resulting in the formation of the final compound, double bonded oxygen, so which is forming the ketone. There are multiple intermediates that are forming here. So among them, the first 3 processes, so how many processes are there? Let's look at one of them. So the first process here, the second process, the third process, and the fourth process. Between 1 to 4 you end up getting acetal. So you start with acetal and you end up with hemiacetal. So you started with acetal and you get hemiacetal. So between 4 reactions, and between 4th, 5th, 6th, 7th, so between 5 and 7 you end up getting ketone. So in simple sense, so you started with a ketone in the dehydrolysis reaction. So from 4 reactions, so between 4 different, so you end up getting 1. So this is number 1. And you have number 2, 3, 4 intermediates. So the 4th intermediate here is you end up getting hemiacetal, OH on one side and OR on the other side. And for the reaction, so you have 4, 5, 6, 7, and finally in the last process you end up getting acetal. OR and OR. So flip the entire reaction, you end up getting the hydrolysis reaction. So this here is the reaction that we just talked about, the entire reaction where we started with acetal, we went to hemiacetal, and then we ended up with the final product, ketone. So let's take a simple example and let's see if we can synthesize this reaction and understand what is the product that forms here. So before doing that, let's also look at the case of enamines and amines. So what happens in enamines and amines? So let's take a look at an imine first. So an imine is a double bonded nitrogen. So under hydrolysis, so what happens here? The reaction again splits this part here. So when it splits here, remember that there are 2 hydrogens here and 1 oxygen. So the oxygen goes to the carbon and the hydrogens will go to the nitrogen. So you end up with double bonded oxygen plus R NH2. So this is the hydrolysis of an imine. Let's look at the hydrolysis of an enamine. So enamine, you have a double bond and you have N bond R. So under hydrolysis H2O, again the same thing happens here. So this is the part that gets cutted out, and 1 hydrogen goes to the carbon here, 1 hydrogen goes to nitrogen, and the oxygen will go to the carbon, the central carbon. So again that also results in the formation of a ketone, plus here you get R2NH. So remember the difference here. When you have a primary amine and a secondary amine. So when you have a primary amine, which is you end up with an imine. So let's put it this way. When you start with an imine, you get a primary amine. When you start with an enamine, you end up getting a secondary amine. So remember these 2 differences here. So if you understand these 2 differences, so that is how you can justify the reactions. So let's take a simple example and let's try to understand this reaction. So this is the question that we have here. So in the question that we have here, so there's a molecule given and they are asking us to undergo hydrolysis. So whenever you see H3O plus, remember that it means it's an acidic medium with a H2O as well. So you are doing hydrolysis in presence of an acid. So now let's try and understand how the reaction works here. So take a look at this reaction and notice what is the group that you have here. So the group that you have here is an ene and an amine group. So there are two groups that you have. So now this is an enamine. So the group that you have here is an enamine, and let's try and hydrolyze this enamine compound. So this is the compound that you have here. You have an ene and amine, and in presence of H3O plus, what is going to happen here? The process where will the bonding or where will the process occur? So this part will disappear, and one of the hydrogens, so in presence of H2O, right? So one of the hydrogens will go to nitrogen, one of the hydrogens will go to this carbon here, and the oxygen will go to the carbon that you have here. So now let's write down the final product that you get from this reaction. So you have an amine, so nitrogen, and you get a hydrogen attached to. Notice that nitrogen has 3 bonds, so it's satisfied. Next, plus, what is the other product that you get here? So here you get a double bonded oxygen. So these are the two products that you get here. So notice that you started with an enamine, so that's why you get a secondary amine and a ketone. So this is the reaction for enamine hydrolysis in this process. So let me give you some examples so that you can try them on your own. So pause the video right here and try to solve this problem. So let me do the first one because it's a cyclic compound. Let me do the first one so that you can do the rest on your own. So let me do the first one. So what is the first one do you have here? You have a cyclic acetal. So a cyclic acetal, what would be the product that you expect here? So let me copy this part. So this is the part that you want here. So first thing that should happen is that notice what type of compound it is. It is a hemiacetal, so which means that the bond is going to break here and so the bond is going to break here and here. So when it breaks, what is going to happen? The carbon where it is breaking will undergo a ketolysis, so where it undergoes a ketone formation. So ketone plus you have the hemiacetal part, so which is this part with oxygens. If you remove that, each of them have to undergo OH formation, so which means that each of them are going to get an OH part on them. So when you remove a cyclic acetal, you get a diol and a ketone. So you get a diol and a ketone. So this is the process of formation of the compound that you have here. Now, so when you want to write down the actual name of the compound, so we can write this as this is cyclopentanone. And this compound you have 3 carbons. So 3 carbons is you have CH3, so CH2, CH2 and CH2 and then OH. So 3 carbon OH is 1,3 propane diol. So these are the 2 compounds that you end up forming in the hydrolysis of the given compound. So now pause the video right here and try to see if you can predict the products that you get in the following reaction. So next let's go on to the topic of sulfur nucleophiles. So ketones and aldehydes react with thiols virtually the same way as they react with alcohols. So remember, a thiol is in place of OH, you have an SH. Right? So replacing oxygen with an SH is what we call a thiol. So if you have a ketone that reacts with a thiol, so that results in the formation of a thioacetal. So in place of RO, you get RS. So OR, you get SR groups, and you end up releasing water. So the same thing when you use it as a diol. So when you use diols, you get cyclic thioacetals. So you end up getting a cyclic thioacetal when you use a diol. Sorry, a dithiol. So when you use a dithiol, you end up getting a cyclic thioacetal, and you end up releasing water again. The same reaction, and both of these reactions must occur in an acidic medium for it to be fruitful. So thioacetals have been commonly used to convert complex compounds into alkanes. So when you use a thioacetal, you can convert a common compound into an alkane using Rene-nickel. So Rene-nickel. So this allows another method for reducing a ketone or aldehyde to corresponding ketone. So first process is the process of thioacetal formation, and then from thioacetal formation, and you end up getting a Rene-nickel reduction. Rene-nickel reduction finally results in the formation of an alkane. So this is a process where you can convert a ketone into an alkane. So remember this process because this can help in understanding synthesis problems. So let's try some examples. So pause the video right here and try to see in this problem. Notice that there are two processes that are occurring. So one is thioacetal and then reduction. So let me do the first problem so that you can try the second one on your own. So this is the compound that we have. So in this compound now, first process is the first reaction is H plus and a dithiol, SH and SH. So how would you do this first reaction now? So remember that dithiols basically split the carbon that contains the oxygen and write it down as a thiol. So a dithiol is formed first. So you have the first compound formation. In the second reaction, we have Rene-nickel. So Rene-nickel, it removes the bond here and adds hydrogen in that position. So that results in so you end up getting hydrogens in the place of sulfur. So this is the final product. Basically, you have two hydrogens in that position. So which you do not need to write, showing because it's an aldehyde. Sorry, because it's a alkane. So this is the final product formation. So this is how you can find the answer when you have a complex problem like this. So make sure to understand this and try to. So pause the video right here and try to solve the second problem and see if you can predict the product in the second reaction. So next let's discuss hydrogen nucleophiles. So recall that aldehydes and ketones are generally reduced to alcohols when you use a hydride reagent. The two common hydride reagents used are lithium aluminum hydride and sodium borohydride. So these are used as the hydride delivery agents. So when you use a ketone or an aldehyde in presence of LaH and water, it creates the alcohol formation. So for an aldehyde, LaH results in a primary alcohol, and for a ketone it results in a secondary alcohol. So that's the difference between the reduction reaction for aldehyde and ketone. So the aldehyde under reduction forms a primary alcohol, and a ketone under reduction forms a secondary alcohol. So these reactions must be carried out under basic conditions because hydrides are really strong nucleophiles. So that's the reason why the reaction favors well when you have basic conditions. So let's take a look at the reaction. Let's take a look at LiAlH4. So that splits to form Li plus and AlH4 minus. So this results in the negative charge where the proton will attack the carbon. So the proton will attack the carbon and result in the combined formation, and this results in the oxygen taking up the electrons from the carbon, and that results in the negative charge on the oxygen, and then under addition of water it undergoes proton transfer. So it undergoes proton transfer where it attacks the proton and results in the formation of an OH group. So this is the process or the nucleophilic process for hydrogen nucleophiles. For the first process is a nucleophilic attack by the AlH4 molecule or the AlH4 ion, the nucleophile, and second one is the H2O that results in the formation of an alcohol. So what happens here? Recall that the reduction of an unsymmetrical ketone forms a new chiral center. So when you have an unsymmetrical ketone and try to reduce it, so the reduction reaction causes a racemic mixture where you create mixture of two R and S mixtures where you have a mixture of stereoisomers. So this is how you could generally create the compound. So let me give you some more examples so that you can try these on your own. So these are some examples that you can try on your own. So let me do the first one. So in the first one, we are adding LiAlH4. So what's going to happen here? So you have a double bonded oxygen. So the double bonded oxygen gets attacked by the LiAlH4, which results in the formation of an oxygen with 6 electron pairs. So what happens here? The LiH4 will attack the carbon. So the LiAlH4, the hydride ion, will attack the carbon, and the carbon will give electrons back to oxygen, so it forms a negatively charged oxygen molecule. Now that under further hydrolysis in presence of H2O, so undergoes proton attack. The negative charge will attack the proton, so the proton will give away its charge. So this results in the final product formation. So the final product formation where you end up getting an OH group on that particular carbon. So this is how the reaction in general occurs. So now in the same way try to do the other reactions as well. So pause the video right here and try to find the products for option B. So products B, C and D. So most commonly Grignard reagent is used to modify the carbon skeleton. So it's generally used to modify the carbon skeleton. So let's take a look at carbon nucleophiles. So when you treat a ketone with a carbon nucleophile, let's take a simple example of a ketone. So let's say we have a ketone. So this ketone under further, so first thing is we are taking in, let's say for example, a Grignard reagent in presence of water. So Grignard reagent, what does it do is it creates a new carbon-carbon skeleton. So which means that now this molecule will result in the formation of a CH3 bond. This CH3 molecule will come to this carbon here, and on the other side you get an OH bond. So this is the group that forms here. So the CH3 ends up forming CH3 here. So the same thing happens when you have a aldehyde as well. For example, let's say we have an aldehyde. So let's say we have an aldehyde here. This aldehyde, under the reaction with CH3, MgBr and H2O, results in the formation of, so you end up getting an OH in presence of the H group, and you end up getting a racemic mixture of this compounds here. Why is it forming a racemic mixture? Because the OH, the Grignard reagent, creates a new chiral center. So the carbon becomes a new chiral center for aldehydes. So this is how you can notice for the nucleophilic attack. So in simple sense, what is happening in the reaction is that when you take a ketone, it's getting attacked by the R minus nucleophile. The carbon gets attacked by the R minus nucleophile, and the group that was originally there will form an O minus compound. So where when it attacks, the oxygen will take up its electrons, which already has 2 pairs. Now we'll end up having 6 pairs with a negative charge. This under further, in presence of H2O, undergoes proton transfer, where the negative charge attacks the proton gives its electrons back to oxygen, forms NOH. So this is a common one that you can notice. So when you use a ketone, so the Grignard reagent creates a tertiary alcohol. When you use an aldehyde, it creates a secondary alcohol. So Grignard reagent creates specific alcohols based on the specific purpose that you are using. So this is how you can differentiate between a ketone and an aldehyde depending on the product that you end up getting. So let's try some examples. So now notice this product here. So in this, let's take the first one. So let me do the first one so that you can try and do the second one. So ET MgBr. So ET represents ethyl. Remember that ethyl is dash CH2 dash CH3. So remember this part. Next you have H2O on the second part. So the first reaction that happens here is the ethyl group attacks the carbon and creates an ethyl group here, and the oxygen will end up getting the negative charge. So notice the ethyl group has 2 carbons. So now you have the oxygen there. Now under further hydrolysis in presence of H2O, so the oxygen attacks the proton gives the electrons back to oxygen. That you end up with the final product. NOH here and an ethyl group on the same carbon. So this is the final product that you get. But notice that this product is going to end up becoming a racemic mixture because it's a chiral center. So it's a tertiary alcohol, but it does end up becoming this structure. So pause the video right here and try to solve these two problems. So the next carbon nucleophile is a cyanohydrin. So what is a cyanohydrin here? So we use hydrogen cyanide as the nucleophile. So hydrogen cyanide is HCN. So hydrogen cyanide, what does it do is that hydrogen cyanide, when you create with alcohols and ketones, will form a cyanohydrin. So what is a cyanohydrin? Let's take a ketone. Let's take a simple ketone. Under addition of hydrogen cyanide, it creates an OH group on one side and a cyano group on the other side. This is an example of a cyanohydrin. So hydrin represents the OH group and cyano represents the cyano. So this is the compound that you end up getting as a cyanohydrin. So cyanohydrin. So let's take the actual mechanism and let's take a look at the mechanism and how it looks like. So you have a ketone, a simple ketone. So this, when you take HCN, so it splits into H plus C triple bond N minus. So this is the compound that you end up getting. Sorry, the minus should be on the carbon with two lone pairs of electrons. So this CN, acting as a nucleophile, attacks the carbon. So again, nucleophilic attack, and the oxygen will end up getting the electrons back again. Right, so now you end up getting a CN that you have here. So C, let me write it as C triple bond N so that it becomes easier to understand. And oxygen ends up getting 3 electron pairs or 6 electrons and forms the structure. Now notice that HCN also has a positively charged hydrogen. So the oxygen now attacks the HCN and takes out the proton and results in the formation of NOH and a C triple bond N on one side, forming the cyanohydrin. So cyanohydrin is a really good compound, and when you have a chiral center, it creates a, so when you have a compounds that we have a complex compound there, it creates a racemic mixture. So most common way in generally doing this, rather than directly, so HCN is liquid at room temperature and is extremely hazardous. So we do not use HCN directly, we use KCN and HCl as a combined product. So when you end up getting the final product, you will end up getting HCl and KCN in the reaction so that you don't have any problem during the reaction. So to make sure that it's not too hazardous, we use this process to create the structure. Now, these cyanohydrins are generally useful in synthesis because they can be converted into other compounds. So when you take a cyanohydrin, under reduction in presence of LiAlH4, so this carbon and this nitrogen gets reduced and forms OH with the carbon that you have here and the nitrogen ending up getting hydrogens. So it makes a single bond and a CO, so carbon and H2 group. So in presence of H2O and LiAlH4. The same cyanohydrin again in presence of H3O plus, which is under acidic medium and heat, forms a racemic mixture of a acid, carboxylic acid. So again, both of them are racemic mixtures. So racemic mixtures. So when you add acid, it creates an acid. When you add LiAlH4, lithium aluminum hydride, or a hydride reagent, it creates a hydride compound. So this is the product that you end up getting. So let's try some examples. So now pause the video right here and try to solve these problems. Notice that in first part you're gonna form a cyanohydrin. Second, they're asking you to reduce, so try to do it accordingly. In the second one you have cyanohydrin formation second, and then at last they're asking H3O plus, which forms a carboxylic acid. So those are your hints. In the first process you get a cyanohydrin, and in the second process you undergo reduction. So in the same here, so this is a cyanohydrin, and in the second process the cyanohydrin ends up becoming a carboxylic acid. So remember the two products. So pause the video right here and try to solve these problems. So next let's look at the Wittig reaction. So just like Grignard reactions, Wittig reactions are also one of the most extremely important reactions. So they were first discovered by George Wittig, a German chemist, so which was awarded the 1979 Nobel Prize in Chemistry. So before his work on phosphorus compounds and his discovery of this reaction, which has enormous synthetic utility. So what is a Wittig reaction? A Wittig reaction uses a phosphorus halide. So phosphorus halide. So what is an halide? So an halide is a neutral compound or a neutral molecule. Let's call it a molecule. A neutral molecule that contains a negatively charged atom directly attached to a positively charged heteroatom. Right, so here in this case the negatively charged atom is carbon and the positively charged heteroatom is phosphorus. So a phosphorus halide is also called as the Wittig reagent. So let's take a look at how the Wittig reagent looks like. So this is an example of a Wittig reagent. So this under resonance can also form a double bonded structure. So these are the stable resonance forms of these two, the Wittig reagent. So how does the Wittig reaction occur? So let's take a simple ketone. So the first process is called cycloaddition. So what happens here is you have a phosphorus group surrounded by 3 phenyl groups. Remember, pH represents phenyl, and you have a carbon with a negatively charged, so phosphorus having a positive charge, carbon having a negative charge with 2 electron pairs and 2 hydrogens. So it undergoes a cyclic addition. So how does the cyclic addition occur? The carboanion will attack the carbocation, and the phosphorus, the positively charged phosphorus, will attack the oxygen. So this creates a cyclic addition structure. So where you have oxygen here and you have a carbon with the phosphorus and has 3 phenyl groups on it. So this is the compound that you end up forming, and this is an intermediate compound and it does not stay stable at all. So what happens here is the oxygen donates its electrons to the phosphorus and leaves. Then this phosphorus again, because the oxygen is donating its lone pair, so this donates its bond back to the carbon, and this then creates the final compound. Notice that here this leaves and this creates a double bond. creates a structure like this. So, and it creates phosphorus with a double bonded oxygen and 3 phenyl groups attached. So this is the total reaction, and the second process is called fragmentation. So in the second process it undergoes fragmentation. In the first process it undergoes cycloaddition, so where it creates a cyclic addition of the compound. So what is the speciality of a Wittig reaction is that a Wittig reaction creates a new C double bond C bond. So it also alters the carbon skeleton, but it rather than altering the carbon skeleton to create a single bond, it creates a carbon double bond. So now let's take a look at what are the major and minor products that you form in the reaction. When you have a complex product, for example, let's say we have an aldehyde. Let's try an aldehyde for once. And let's say the compound that you have here is CH3, and on this side you have a double bonded PPH3. So in this reaction, what is going to happen again? Notice that the carbon here, this carbon here will attack this carbon, and the oxygen will leave with phosphorus. So this creates the final product. So where it creates a double bond there, and on one side you have CH3, on the other side you have H. So CH3, H, right, and H here. Now the question that should ask is that, is it gonna form an E product, E isomer, or a Z isomer? So depending on the compound that you use, the most common major product is the Z isomer. So it generally creates the Z isomer most commonly. But again, that depends on what type of groups that you have on it. So if the group that you have on the carbon, so if the compound, the groups that you have, if it is an electron donating group, you end up creating a Z isomer. If it's an electron withdrawing group, you create a E isomer. An example of an electron withdrawing group, you can consider that to be a phenyl group or a chlorine. Anything that has a lot of electrons will end up creating electron withdrawing group, so which ends up creating any isomer. What is the Z isomer here? Notice that the two main groups are on the same side of the double bond, so that's why it's a Z isomer. If they are on the opposite sides, we create the E isomer. Let's take an example of an E isomer and let's see if we can try to replicate the reaction. Let's take the same compound. So in this reaction, let's consider that you have a benzene on one side. So notice that the benzene is an electron withdrawing group, so which means that it's going to end up having to form a E isomer, so which means now this is the double bond, so which means that if this is the double bond to form an E isomer, so this side you should have to get the benzene atom, and on the other side you should get the hydrogen. So this is the reaction. So this is the E isomer. So this is the major product, an E isomer. So depending on the product that you are using, and depending on whether it is an electron withdrawing group or an electron donating group, you end up getting the final product. So let's take a simple example and let's try to see if we can find the product of this reaction. So let's try and solve this problem. So the first thing given, so you have the compound and they are asking you for this is the product. Now notice that this is the carbon that you have on the other side, which means that there is a carbon there. Now let's try and understand the reaction. So you have a cyclopentane that's attached to a double bonded oxygen with a CH3. So which means now the reaction occurs, it creates a double bond where the ketone is. So this double bond will stay the same. Now look at the group. So is it an electron withdrawing group? So it's an electron donating group. So which means that it's going to end up forming the Z isomer. So the Z isomer will create the groups on the same side. So which means on this side you end up getting CH. So this carbon is the CH, so which means that you are going to end up having CH2, CH3 here. So or you can write it this way, CH2, CH3 here, and on this side you have a hydrogen. Notice that this is the carbon that's gonna bond here. So this is the carbon that you have here, and the hydrogen, this is the hydrogen that you have here. So the CH2, CH3 group is the one that you have on this side. So notice that both the important groups are on the same side, so which means this is a Z isomer. So this is going to be the major product. So this is how you can form the reaction. Now, so let me give you some problems so that you can practice them on your own. So pause the video right here and try to solve these two problems. So try to solve these two problems. If you are comfortable with those two, try to solve the last one. So pause the video right here and try to solve these problems. So next let's take a look at the next reaction, Baeyer-Villiger oxidation. So an oxygen is generally inserted into an aldehyde or a ketone group between a carbonyl carbon and a neighboring alkyl group. So what you are doing here is you are converting an aldehyde, so a ketone becomes an ester and an aldehyde becomes a carboxylic acid. So that's the idea behind the formation of Baeyer-Villiger oxidation reaction. So in this reaction, when you use a cyclic ketone, it produces a lactone. Lactone is a cyclic ester. Right? So for an aldehyde or an unsymmetrical ketone, the rate of migration is as follows. So hydrogen is the one that's the greatest, tertiary in a second, and secondary the last. Next you get phenyl first, primary later, and then methyl first. So this is this. You use this trend to determine the regioselectivity of where this particular oxygen is going to end up forming. So using this trend, how do we create the regioselectivity here? Let's take a look at this compound here, and under presence of a peroxy acid, where should the oxygen go? So the oxygen always goes towards the one that has a tertiary carbon. So this is a tertiary carbon. Notice that this is a tertiary carbon, so that's why the oxygen will end up going there towards that side. Right? So in this slide again, on the other side you have, in the second trend you have a hydrogen here. So hydrogen gets higher priority than a secondary carbon, so hydrogen will go, so the oxygen will go towards the hydrogen side. So this is the principle that you have to use to determine the regioselectivity. So always hydrogen first, then tertiary, then secondary, and then if you have a phenyl group, then phenyl, and then primary, and then finally methyl group. So this is the directions in which we have to look for. Let's finally talk about synthesis strategies. So recall the questions that we discussed during synthesis. There are two questions that you have to ask. Is there a change in the carbon skeleton, and is there a change in the functional group? Now, one of the common reactions that we have seen here is, one reaction that is useful is the Grignard reaction, and the second one is the Cyanohydrin formation and the Wittig reaction. All these three reactions are commonly used to change the carbon skeleton, because the combination of this Grignard reaction creates a new single bond carbon reaction. Cyanohydrin creates another carbon chain reaction, so you have extra carbon attachment, and finally Wittig reaction attaches a C double bond C carbon. So new double bond, and this is the reactions that we generally see. So we have seen the common reactions from before, where we used single, double and triple bonds to form ketones, alcohols and alkyl halides, and we are going to end up extending that reactions to the reactions that we have covered in this lecture. So this is the summary of all the reactions that we have seen in the lecture. So use this as your basis when you are synthesizing compounds. So try the reactions. So let me give you some more examples so that you can try them on your own, and try to see if you can synthesize this particular compound. So this is the Wittig reaction example. Try this compound. This is the Baeyer-Villiger reaction, and try to finally do the synthesis reaction. So if you're not familiar with this synthesis reaction, you can go through the textbook and you can find the answer and understand how the synthesis occurs. So with that, we end our chapter on aldehydes and ketones.